Thank you for the introduction, and I would also like to thank Dr. Dhillon for giving me this opportunity. Today we are going to look into some aspects of dynamic spectrum access in which we will specifically see what kind of authentication requirements are there in dynamic spectrum access. Now we will start with the idea of dynamic spectrum access, and we will look into the challenges in it. Then we will look into what is the requirement for privacy preserving authentication in dynamic spectrum access, and then we will look into the challenges in the developing a privacy preserving authentication scheme. Then we will see what we proposed as a solution for this privacy preserving authentication. And the most interesting part of the talk will be that how we actually used the idea of signal processing, specifically the idea of spreading codes in direct sequence spectrum systems into cryptography and solved a difficult problem. So that will be the main focus of this talk. And at the end, we will also look into the future direction of my work. So to get started, first thing, most of you already know the need for dynamic spectrum access. Here you have two types of, to actually come up with an efficient way to use the spectrum, we need to come up with this idea of dynamic spectrum access. In dynamic spectrum access, you have two types of users. One is a primary user who actually owns the license to use the spectrum. And then there is another set of users, which are secondary users, which use the spectrum when the primary user is not using the spectrum. Now we could divide the whole concept of coexistence of these primary user and the secondary user into two coexistence scenarios. The first one being when commercial users are sharing the spectrum with other commercial secondary users. Now the other scenario could be the federal or state users who are the primary users. They are sharing the spectrum with the commercial users. Now when we consider the second scenario, when the federal users are sharing spectrum with commercial users, the government has taken, the USA government has taken many steps in enabling that scenario. A few of those steps are here. The first one was in, not the first one, but the most important first step was in March 2010 when the FCC came up with this national broadband plan that they would like to open up 500 megahertz of band. Then came the PCAST report, which actually put up the roadmap for opening up the dynamic spectrum access for federal spectrum. And then recently in April 2015, we have this final version of NPRM, which said that this 3.5 gigahertz band could be used for commercial purposes. And 3.5 gigahertz is generally used by the radars of the federal government. Now when we look into this scenario where the federal government, for example, the radars which are of the naval radars which are going to share the spectrum with commercial users, then there are many security issues related to that. And in my advisors, Dr. Park's group, we work on different parts of that problem, how to counter the different threats that we have in that kind of sharing scenario. My work is specifically, and the focus of this talk is specifically related to the threats by rogue transmitters. So for instance, in a scenario where the rule has been made by an FCC that the secondary user should not transmit when the primary user is transmitting. But what happens if there are some rogue transmitters or rogue secondary users which will not follow this type of rule, and they still send transmissions over there, and that will cause interference to the primary users. So in that scenario, in order to prevent or deter that kind of scenario, we need to come up with a transmitter authentication scheme. So we need to come up with different aspects to actually enforce that kind of rule. But one of the important parts of that enforcement network will be a transmitter authentication scheme by which we could actually identify and authenticate the transmitter which has caused that rogue transmission. So when we look into the transmitter authentication in dynamic spectrum access, there are multiple challenges into it. But the basic idea for doing transmitter authentication is that you have an authentication signal, and you want to embed that authentication signal into the message signal. The message signal is the data that a transmitter wants to send to a receiver. So for example, a secondary transmitter is trying to send some message signal to a receiver. Now what it needs to do for enabling authentication in this scenario is to embed an authentication signal into its transmission so that it could be authenticated. So when we consider this idea of authentication signal, there are two processes that needs to be done at the transmitter. The first one is the generation of the authentication signal, which means that you need to generate a sequence of particular bits which will identify the transmitter. And then you need to actually embed that authentication signal into the message signal. Now the regulator, which can be a sensor put for the enforcement in the whole network, now it has to do again two operations. The first one being the extraction of the bits from the received signal, and then using that bits it needs to identify and verify the transmitter. So we can divide this whole problem into two parts. One is a PHY-layer scheme, which will be used by the transmitter for embedding the authentication signal into the message signal, and then an extraction mechanism in which the regulator could extract that signal. So this is here what we need to see is few things that are the requirements of a dynamic spectrum access scenario is that the regulator will not be the intended receiver. So, so consider this scenario that there is a network of secondary users, they are communicating among themselves, but the FCC has put some sensors around. Now you have technologies like beamforming and other technologies by which the transmitter can actually transmit its own signal and put most of its power towards their intended receivers. So the sensors that will be put by the FCC will receive very low signal to noise ratio, the signals with very low signal to noise interference ratio, because they will not be the intended receivers. Also, this secondary user network, they may communicate among themselves and decide on a particular set of parameters that they want to use based on their channel. Now, the sensors which are being put there by the regulator, they will also not know the parameters which have been agreed by the secondary user network. Therefore, the secondary user, therefore the regulator has to do this authentication blindly, has to extract the authentication bits, authentication signal blindly. We call it blind. Now, as I already said, that it should be also robust against harsh channel conditions, which means fading and low signal to noise ratio. And also it needs to have a very low overhead, because this is one more type of authentication that we are imposing on transmitters. So it needs to have low overhead. So data rate, low, it should not affect the data rate, it should not affect the power. Now the other type of challenge in this is to develop an authentication scheme. Now what we have done by using a PHY-layer scheme is to give every transmitter a technique in which it could embed its identity into the message signal, and it can transmit. And by developing an extraction mechanism for the regulator, which is a blind regulator, which will actually identify the transmitter without knowing many of the transmission parameters. So what we have created a scenario is that any receiver which has the capability to demodulate and decode any signal will be able to eavesdrop on the transmitter. So wherever such a transmitter will have, the scenario will be that if there is a secondary transmitter roaming around in area, any receiver will be able to find its identity, and it can know when that transmitter is operating, at what time, at what place, and so there will be security threats related to the privacy of the transmitter. So there is not a trade-off, but both of these things should be together in a dynamic spectrum access scenario. One is an PHY-layer scheme, so that the regulator could actually extract without knowing a lot about the transmission parameters, and then there should also be a privacy-preserving authentication mechanism. Now, this is the first part. This was my previous work, which is the actual PHY-layer scheme by which you could actually embed the authentication signal into the message signal. I have put here just for completeness, but we will not go into the detail of it. So this is the PHY-layer scheme is very simple. So what you do is you have the message signal as samples of an OFDM. So we assume that the transmitter is using standard OFDM signaling. So now the message signal is what the samples of an OFDM signal. Now, usually the transmitter sends all the messages in frames. So the message signal is divided into frames. Now you have a sequence of bits. At this point, we assume that the sequence of bits is just a random bit. Later, we will see what kind of authentication signal needs to be generated. But at this point, we assume that it is just a random sequence of bits. Now it has to embed that authentication information into the message signal. So what it will do, it is the very simple scheme is that each frame, the frequency of each frame will be shifted by in one direction for embedding a bit 0, or the frequency of that will be shifted in another direction by a small margin for embedding a bit 1. So what you will see in, if you see the spectrum diagram of the signal, is that the signal is moving slightly in both the directions when the authentication bit is 0 or the authentication bit is 1. So this shift will be detected by the receiver, and they will be able to identify the transmitter. Now, few things that we need to underline here is that this small amount of frequency shift that we are embedding is not going to affect the intended receivers. Why? Because every transmitter has an oscillator to upconvert the signal to a center frequency. Now, these oscillators are, although they are very properly designed, but they still have some amount of error. So, for example, IEEE standards allow that those kind of oscillators can have an error of 25 ppm, which translates into 60 kilohertz for a center frequency of 2.4 gigahertz. So, an oscillator could be designed with this much frequency offset. But usually what we have in market will have very low. Generally, Cisco claims that they have oscillators with 1 ppm, which means that we have a very long margin of error between the actually designed oscillators and the IEEE standard. So we could use that small margin to actually embed the authentication signal. Now there are few steps that needs to be done by regulator, which has to do it blindly, and most of you would be knowing many of these steps is like signal detection and sampling. Then it will have to do symbol synchronization, which means that it needs to find the FFT size, cyclic prefix size. Then it also needs to do frame synchronization, which means that it needs to find the frame boundaries of the message signal that it is receiving. And then finally it will extract that frequency offset, and then it will be able to identify the sequence of bits. So this is now I'm going to the more interesting part, which is the privacy preserving part of this whole problem. Now, in a privacy preserving setup, you have 3 entities. First is the signer, who is the transmitter which wants to generate an anonymous digital signature. So what digital signature means is, you could just by the term of signature, you could relate that if you have a document, a human signs the document at the end of the document by his signature. So digital signature is just a digital format of that if you want to send a message, what you do is you sign it with a sequence of bits. So that is a digital signature, and it needs to be anonymous because you want privacy to be inbuilt into this mechanism. So it has to be an anonymous digital signature. So now what the verifier needs to do, what the verifier needs to do is to verify that this signature is valid, but it should not actually know the identity of the transmitter. Okay, so let me give you an example. So let's say the FCC gives a few secondary users a license for a year to operate in an area. So now the secondary users have a license for an year to operate in that area. Now what the verifier needs to do is to just check that the secondary user is embedding that type of license in its signals. So the verifier will look into that, along with its identity. So verifier will look into the authentication signal that it is receiving. It will extract that okay, there is a certificate embedded in it, that it is valid for 1 year. But now what the signer does is it uses a function. We will see what kind of function can be used. It uses a function to hide its identity. But the verifier claims that still there is an identity related to this certificate that it has, and it is a valid identity. So the signer has to verify that it has the license. The verifier has to verify that yes, the license that has been transmitted by the signer is the correct license. Now we have a group manager who is like an FCC, which knows that how many licenses have been provided and how many keys have been given to these signers. Now this idea of privacy preserving authentication can be applied to obviously dynamic spectrum access, but there are other ways in which you could actually use this idea. And one of the very important fields is intelligent transport systems, where you have humanless driving cars. So if the cars are talking to each other, but we need to ensure that the cars do not send their identity to other cars. So that the movement of car or where the car is traveling to and at what time the car is traveling, so this should not be known. Now any topic becomes more interesting if you add a term called Internet of Things. So we have added that term as well, that it could also be used for privacy preserving authentication in Internet of Things. Now if you look into the existing literature, you could see that there are mainly two aspects of doing this privacy preserving authentication. One of the ideas is very simple. What you do is you give every signer a large number of identities, not just one identity, but a large number of identities called a pseudonym, and tell it to change it after some time. So for example, that we already said that a secondary user gets a license for a year. So the FCC gives it let's say 365 identities, and so every day that secondary user changes its identity. Now so for one day it will be identified as a secondary user who is transmitting, but when it changes it to the another day, others will not be able to know which is it the same secondary user that was transmitting the previous day. So this is a very intuitive idea of preserving the privacy, that you give 365 identities. Now in order to make that possible, you need to in order to make this authentication possible, you need to also give it 365 private keys, 365 public keys. I will not go into the details of these keys, but it's just there to show that you need to provide a lot of information to the signer if you use this idea. And the drawback comes from this thing, that you are giving a large number of identities to every signer and a large number of keys to every signer. So it becomes a large communication overhead, which depends not only on the number of users in the network, but also the number of identities that you give, the number of pseudonyms that you give to each one. And key management also becomes a difficult problem. So there is another set of schemes which are called group signatures, which have some solution to this problem. So in group signatures, what you do is you give only one key to the user, and the user generates a group signature on behalf of group, which means that let's say in the scenario of spectrum sharing, we can say that the secondary user just proves that it has the license to transmit for a year. It does not, it makes a group signature means that it just mentions that it has the license for operating for 1 year. It does not reveal its identity completely, and it hides that identity behind a function. Now verifier, what verifier does is, verifier does two things. Now before going into what the procedure for the verifier is, I will just mention one more thing. Now consider this scenario that there is a network of secondary users and FCC has given license for 1 year to all the users. Now after a month or 2 months, some of the secondary users perhaps do not pay their bills, or some of the secondary users were caught doing some interference. So now since they have already obtained the license for a year, what is the option for the FCC in order to just stop their transmission? The FCC cannot directly go physically and stop their transmission. So what the FCC can do is to publish a list, which is called a revocation list. Now every verifier, what a verifier can do is, if it receives a signature, it takes it and just sees that okay, it is valid for 1 year. Now it also goes to the revocation list and tries to see if that identity is included in that revocation list or not. So that is what the need for revocation list is. That if you have given a certificate to a user to actually transmit for a period, but you want to break that, you want to make that period smaller, so you use the idea of revocation list. Now here comes the problem. In group signatures were able to solve the problem of large communication overhead. But the problem comes when you have a revocation list. Since the identity is hidden behind a function in the signature, the verifier cannot directly use the signature to actually find whether the identity is included in it or not. So what the verifier does is it runs the function and then checks whether the function gives a particular value or not. Now these are cryptographic functions which are very computationally extensive. So we ran one of these functions, only one instance of that function on an Intel i7 processor, and it takes 2 milliseconds to run one operation. So assume that you have a network of secondary users with, let's say, 1,000 revoked users. So suppose in an area you have secondary users in hundreds of thousands, and you have 1,000 revoked users. Only thousands have not paid their bills or whatever. So you put those 1,000 identities in the revocation list, but now every signature will need to go through. Now every identity needs to be checked and used, and that function needs to be run on every identity sequentially throughout the revocation list. So you will be taking 2 into 1,000, 2,000 milliseconds, which means 2 seconds. Now here 2 seconds does not matter, may not matter depending on the scenario that you are using. If we assume of a scenario where, let's say, there are cars moving on a street. Now, if a car which is moving at the front of another car brakes, and so these are humanless cars. So they are automatically transmitting signals to each other, and they are collaborating to move on the street. Now a car puts a brake, so it will send that signal that, okay, it will broadcast that signal that I am braking. Now the car which is behind that car should receive that signal and take further action, which means that it also has to brake. Now if it receives the signal that the front car is braking, it has to verify that, okay, this signal is correct. Now if it takes 2 seconds to verify that that signal that the front car is braking, then it will be, depending on the speed, there might be a collision. So 2 seconds might be a very large time depending on the applications that we are looking at. So we need to reduce that. Now we came up with a scheme to actually reduce it, and we did it by which is called group signatures with probabilistic revocation. So we used 2 ideas. The first idea was that those identities should not be hidden behind a function. They should be revealed. Now you cannot, so what we did was we used the idea that now in group signatures you cannot reveal the identities, but what we did was we added some type of alias tokens which are also somehow related to the identities. We will see what are the actually the values for alias token. Now the first step was to reveal a particular token in each signature so that the verifier does not have to go through computing that computationally expensive function. Now the second thing that we did was, rather than going through checking the revocation list sequentially one by one, you check the whole thing in a single step. So that was the major idea behind coming up with this scheme, that you actually do it in a single step. Now before going into the detail of this scheme, I would like to bring up an example that if you, in a math, it is a very well-known example in mathematics, that if you want to check if a number is prime or not, it is very difficult to do if the number is very, very large. So if I just tell you that whether 1113 is a prime number or not, the basic thing that you will do is let's divide it with 2, let's divide it with 3. But there is till very recently, till 2002, there was no very efficient algorithm to actually deterministically find if a very, very large number is prime or not. Now, 2 scientists, Miller and Rabin, they came up with a probabilistic algorithm that although you cannot find that a number is prime or not, but you can tell with some probability that whether this number is prime or not. So the algorithm that they proposed, they came up with this idea that, okay, if we run this algorithm one iteration, I can say that this number may be prime, but I may be wrong by a probability of 0.25 or 1 by 4. So it says that I may be wrong by 1 by 4. Now if you run it the other next time, the probability gets squared. So it says that the algorithm says that it may be a prime, but I am maybe wrong by probability 1 upon 4 whole square. If you run it by 10 times, the probability will be 1 upon 4 raised to the power 10. So this is a very efficient algorithm, and if you run it multiple times, the probability of making an error will be very, very low. So we use this idea, and we solve this problem of actually going through sequentially into the revocation list, and we came up with this idea of using it single step. But we will do it with a probability, and if we run it a sufficient number of iterations, we will be able to solve the problem very efficiently. So there are a few algorithms involved in it. So rather than going into the maths of this problem, I have just put what are the basic ideas behind this problem. So definitely this is a very math intensive problem, but the basic ideas are very simple. So first algorithm is the key gen algorithm, which means that group manager like FCC allots generates a group, clubs together many second users together in a group, or possibly in an area. All the second users in an area can be clubbed together in a group, and it generates a group public key, which means that a whole certificate for that area. Now there is a join, which means that the secondary users get their identities. So here what we do is we again assume that the group manager allots a number of identities, a large number of identities to each of the signer. But what it does is it gives only one private key. It is not like the pseudonym-based scheme that you have many identities and many keys. You have many identities, but you have only one key. And these many identities do not need to be transmitted to the signer. It can be generated by the signer itself. It will just need the key at its end, and it will be able to generate its own identity. So the communication overhead is definitely lower than the pseudonym-based scheme. Now signature. Now in the signature, what the basic idea is that it has to include its alias token, which is just a form of identity into the signature. And the verifier has to do two operations. One is to check for the validity of the signature, whether the signature is valid or not, and the second is to check whether whether the signer is revoked or not revoked. Now another algorithm is revoke, where the FCC can revoke the secondary users. That is an algorithm. And then there is an algorithm open by which that FCC can actually identify. So you need to have an inbuilt mechanism in which if there is an interference event, although any receiver could not be able to identify the transmitter, but the regulator, who is the FCC, should need to identify who the culprit is. Therefore, there needs to be an open algorithm which could be run only by the group manager, like FCC. No other verifier can run that algorithm. So I have not put any maths in this whole presentation. This is the only slide with the math. It is just to explain the idea of one of the contributions. So here the basic idea is you define a function which is called bilinear map E. And what the function does is, if you run that function on u raised to the power a and v raised to the power b, what it gives out is E, the function of u raised to the power v, u comma v raised to the power ab. So the basic methodology which are used by the group signatures to come up with a good scheme is that you choose any random r and generate a value u, generate a value t1 is equals to u raised to the power a divided by r, and then you generate a value t2 which is v raised to the power br, and then you again generate a value h which is the function of u v raised to the power ab, and provide t1 t2 h as part of a signature. So what the verifier does is it verifies whether if you run the function e t1 t2, whether it is equal to H or not. Now, which has to be true, because if you see that u raised to the power a divided by r and b raised to the power br, when you multiply the exponents a divided by r and b raised to b into r, the r will get cancelled out and it will be equal to the value h. So that is the basic idea, and that will be applicable for any random r. So that was the basic idea for the standard group signature schemes. So what we did to change this type of to actually come up with a scheme is that the group manager allots a particular set of values r. So the signer cannot just randomly choose any r. So it gives a particular set of these values r, and a private key which is related to these values. Now, if the signer uses these one of the Alias tokens from this set, the signature will be valid. But if it chooses any other random value, the signature will not be valid. So therefore, this embedding of Alias token is enforced on the signer. So that was one of the contributions, which is basically the cryptographic part of this problem. Now the second problem is the most interesting one, and I can say that it is the most, it is what I wanted to present in this wireless activity seminar, that the idea of Revoke algorithm. So what the idea we came up with, that what you do is you have Alias tokens as sequence of bits. Now you map it to an Alias code, and we will see what that Alias code could be. And then you generate a revocation code from that Alias code. So we looked into different types of mechanisms that could do that, and we looked into the direct sequence spectrum, which is used for 3G mobile communications. So there, many of you know that there are different types of codes that are used to actually cancel the interference in the system. So when at the downlink you have orthogonal codes, and at the uplink you have pseudo-random codes in DSSS systems. So they are used so that multiple signals are overlapped over each other in time and frequency. So multiple signals are overlapping in time and frequency. Multiple signals which will be first encoded with these spreading codes, and then they will be overlapped in time and frequency. But a specific signal can be extracted from the received signal if you use the same spreading code. So the idea here was that you have overlapped signals in time and frequency, and you could extract one signal from it. So that was the basic idea. Now our problem was we wanted to do one-shot revocation check. So now you could relate that what we will be trying to do, that what we will do is we will overlap all the identities in the revocation list. So we will not have a list. We will overlap all the identities in the revocation list, and then we will try to extract whether whether an identity exists in that overlapped version or not. So now the basic algorithm that goes behind it, that the Alias tokens. Yes.
You are then assuming that all the identities in the revocation lists are almost orthogonal, right?
Exactly. So we will go back. So next slide is the design of those orthogonal codes, and we will see what type of codes can be used.
Okay.
Yes. So yeah, that was also a very nice problem to solve. Yes. So here, what will happen is, as Dr. Dhillon was mentioning, that when you actually add all of them, and you want to extract one of them, what you do is you just compute a cross correlation of the identity that you want to check. So you have the verifier receives a signature, and the signature has an embedded Alias token in it. So it will map that Alias token into an Alias code, and then it will compute a cross correlation of that Alias code with the revocation code. And if that threshold is above a certain value, it will say that that Alias code is in the revocation code. But if it is not, then it will decide that. So if it is, if the Alias code exists in that revocation code, which means that this signer has been revoked. So, and if it is below that threshold, it will be decided that this signer has not been revoked. Now the design of alias codes was very interesting. So first thing that we need to see is, for an orthogonal code, the length of the orthogonal code is equal to the number of orthogonal codes that you could generate. Now for security reasons, the signature, the alias token that we used in these signatures has to be at least 160 bits long. You might have seen on your when you go for on a website that your ID is your credit card is encrypted or 128-bit key encryption. Those kind of messages you must have seen. So people have decided that 128-bit is not sufficient, and they are moving for larger sizes of keys. So with the current estimations, we assume that if you use 160-bit long keys, it will be safe. So if it is 160 bits long, there are 2 raised to the power 160 possible alias tokens, and therefore you need to have 2 raised to the power 160 possible orthogonal alias codes if you want to have all the alias codes to be orthogonal to each other, which will mean that you need to have an orthogonal code of 2 raised to the power 160 samples long, which is definitely not possible, and it is not possible to come up with a technology to store or to process that. Now, if we use non-orthogonal codes, which could be pseudo-random or completely random, this will lead to a probabilistic algorithm. Now, probabilistic algorithm means that you could have 2 things: false positives and false negatives, which in this case will be that if there is a valid signer and you claim it to be revoked, so that is a false alarm. So the valid signer is claimed to be revoked. That will be a false alarm. Now there could be a false negative where a revoked signer is declared to be valid. Now if you have a false negative where a revoked signer is declared to be valid, that is a security threat that a culprit has been just allowed to transmit. So you cannot have false negative in any scheme. Therefore, but all the pseudo-random, if you use any of the pseudo-random or the random codes, you will have both of these two, false positives and as well as false negatives. So therefore, we came up with this idea of piecewise orthogonal alias codes, which means that what you do is you divide this alias token into multiple segments. Now, let's say if it is 160 bits, we divide it into 16 segments, each of 10 bits long. Now, each segment is mapped to an orthogonal code now. So you are mapping only 10 bits to an orthogonal code. So the length will be 2 raised to the power 10 for each orthogonal code. And then you concatenate all these orthogonal codes. So the total length will be 16 into 2 raised to the power 10, which is manageable, which is definitely manageable. Now the interesting part of this whole design was that the results did not include any false negatives, which was a very significant contribution, that there would be no false negatives. So here is an example to illustrate this idea. So at the bottom you have a table and you have 2 segments. So S1, S2, S3, S4 and S5 represent the alias codes, which are composed of 2 segments of orthogonal codes. Now the regulator wants to revoke S1 and S2. So the revocation code RC is the sum of S1 and S2. Now if you compute the correlation of this RC with each of them, S1, S2, S3, S5, you will see that if you compute the correlation of both the segments separately, you will see correct detection for S1, S2 as well as S3. So 1 denotes that the verifier determines that okay, it is a revoked value, S1 is revoked. Now again, for the S2 it gets 1, which means that it is revoked, which is the correct detection. Now for S3 it gets 0, which means that it is also correct detection because S3 was not revoked. Now for S4, the correlation comes out to be 1 and 0. So if you correlate only the first segment, it will be 1, which means, and if you make a decision based on that, it will be a false alarm. That although S4 was not revoked, you will make a result that it is revoked. But if you go on and you also use the second segment to actually calculate the correlation, you will again get a 0 and you will claim that okay, yeah, so even if there is 1 0 in this whole sequence of correlation, you will claim that this is not a revoked identity, so you will be making a correct detection. Now for S5, for both the segments, you will have 1, 1, and there will be a false alarm. So there will be false alarms in this system, but there would never be a false negative. Now, these are few plots which show the probability of making false alarm in this design of piecewise orthogonal codes. So, so there are two parts of this piecewise orthogonal code. One is the length of each segment, which means that the length of each orthogonal code and the total length of that you go on for. So what we are assuming here is that if I go back here you see that even if you do not, so for the S3 you could see that if you check for the first segment only, you can get a 0, and you can directly make a conclusion that the S3 is not revoked. So you do not need to go on for all the segments to actually compute the final answer. You can make that conclusion much before it. So you have two things that you could change here. One is the length of each orthogonal code that you are using, and the number of orthogonal codes that you check for. So you do not need to check for all the orthogonal codes that are concatenated in the Alias code. You can make the decision even before that. So in both the cases, if you increase the right hand side figure shows if you increase the number of bits in each segment, what we are doing here is we are increasing the length of the orthogonal code. So if the number of bits in each segment is increased, so let's say if we increase, so earlier we are using 10 bits for each segment, so the length of the orthogonal code was 2 to the power 10. Now we used 20 bits in each segment, so the length of the orthogonal code would be 2 to the power 20. Now what we are doing is we are increasing the orthogonality feature of this piecewise orthogonal code. So the total length would still be represented by 160 bits, but there is a nice trade-off between what you could do with those 160 bits. How you divide that 160 bits into the number of segments and the length of each bit. So we looked into those trade-offs, and actually here I have not shown it, but we decided that if the number of if you want to have a particular amount of probability of false alarm, and the number of revoked users in the system is a particular number, then you can come up with an optimum value for choosing the size of the segment that you want to use. So you could actually come up with that value.
So this also depends on the total number of users, right? So
yes, it also depends on the total number of users. Yes. Therefore, there are two curves in both the figures. That if the number of users increase, then the probability of false alarm will increase.
Yes. So you said that when you were mentioning about this 160-bit requirement, right? So you said that you need 2 to the power 160 length for the orthogonal codes.
Yes.
That is necessary only when you have 2 to the power 160 users.
Yes.
If you have less number of users, you obviously don't need that many codes, which means you can shorten the length.
Yes.
So I couldn't really get that argument.
Okay, yeah. So that is related to the basic methodology to have this cryptographic algorithm. So in cryptographic algorithms, what you need to do is you have a set of numbers, so a set of numbers represented by 160 bits. So what you do is, there is no structure to select a particular value from that set. So what you do is you randomly select a number. So you randomly select a number from that 160-bit valued number. Now that number could be anything. Now since that number could be anything, therefore the Alias code that you design should match to that number. That number could be anything. So if the set was 160-bit long, but you are always using a subset of, let's say, only, you are not using 2 to the power 160 values, you are using only a small value, then you could have designed a smaller orthogonal code. But for ensuring security of this mechanism, you have to randomly choose one of these 2 to the power 160 values. You cannot just, and therefore the design should be for 2 to the power 160 combinations, yeah.
Right. But in your design as well, you are mapping a few of those combinations into a single value. That's why you're getting false alarms.
So let me see that. Let me tell you here that here the length that I'm saying, that 16 to the power 10, that is the length. but if you see the number of combinations that it could support, it will still be 2 raised to the power 10 raised to the power 16. So it will be still be 2 raised to the power 160. So it can still support 2 raised to the power 160 combinations, but the length will be 16 into 2 raised to the power 10. So that is the therefore it is a probabilistic algorithm. So it still supports 2 raised to the power 10 into raised to the power 16, which is 2 raised to the power 160, but the length is smaller now.
Right.
Yes.
So all these codes are orthogonal, but internally there are some pseudo codes combined, right? And then we, based upon one strength, the correlation strength, we decide whether it falls into the list or not.
Yes.
So how do we decide this the threshold? Because if the length is different, the threshold will be different.
Yeah.
If the
So,
length of the pseudocode is different, the threshold is different.
yeah, that is also a very good question. So that's what we also thought. But the good thing about orthogonal codes is that if the correlation, if you correlate two orthogonal codes, if both are same, then the value will be the average value will be 1. And so let me just tell you. So now you have multiple codes. So if you wanted to compute the correlation of complete code, you might have got different values. If there are 10 orthogonal codes which are concatenated, you might get 5, you might get 6. It depends on the orthogonal code that you are using. But to make a decision whether Alias code, the concatenation of 10 orthogonal codes is revoked or not, you have to just get one value. So the threshold is 1. So you have to just obtain whether it is less than 1. So the threshold is 1. If you get a value 0, which means that it is not revoked. If you get a value 1, you decide that it may or may not be revoked. So you go on to the next orthogonal code. You go to the next segment. You again check that segment. You again get a 1 or a 0. So if it is again a 0, you decide that it is not revoked. But if you get a 1, you say that okay, it may be revoked. You again go for the next segment. So you keep on going. We are not computing the correlation over the whole segment. So you are not getting different values. So definitely, if you would have computed the correlation of the whole sequence, the values would have been different.
But as you're saying, is a trade-off. If you increase the length of the orthogonal code,
Yes.
the error rate will increase, right? The
Error will decrease. If you increase the length of the orthogonal code,
the error will decrease for the system on the whole. But when you want to find threshold for a pseudocode of this much length, because the correlation values might not be that proper. Because if the pseudocode length is smaller, we'll be able to, the correlation values are proper, and then we can detect it in a better way.
so that may be true for a random code. So if you go into the design of orthogonal code, you will see that is, so you're right. If you use a random code, and if you use a very large random code, and then you calculate the correlation of those large random codes, then you will get a very close values. But if you use shorter random codes, they will have very different values. But orthogonal codes are designed in such a way that their correlations are always either 1 or 0.
Okay, these codes are really decide the determination.
Yeah. Yes.
Like
Yes.
marker or CCK, which we use in DSS.
Yes.
The standard DSS spectrum uses.
Yeah. It is. So that's what I said at the beginning, that these are spreading codes.
Yeah.
But we looked into the spreading codes and saw that orthogonal codes cannot be used because of this reason, and the other codes which you are saying, this M codes and others, those cannot be used because of this reason. Yes. Yeah, it is similar to those kind of codes. Yes. So we are already close to the time. Yeah. So let me just go into just this one curve. So this is an example of GSPR, our proposed scheme in intelligent transport system. So in intelligent transport systems, what happens is in each 100 milliseconds, you need to transmit a signal saying what you are doing with in your car. So these cars are all humanless cars. So these cars need to transmit a signal in each 100 milliseconds. And we compared our scheme with the existing schemes, and we showed that if we use our scheme, you could support 10 cars around you without any message loss. So message loss means that if you could process a message within 100 milliseconds, then you could actually take an action. But if you could not process that message in 100 milliseconds, so that is a message loss. So we showed that with our scheme, you could actually support around 10 cars around your car. But with the existing schemes, there may be either 1 or 0 cars that you could support. So that was one result from this. Now to conclude the talk, so this is the curve for the computational overhead of verifying if a signature is correct or not. So what we did was, at the right hand side, you could see that, and on the x-axis is the number of revoked users. So what we did was, if the number of revoked users is large in the network, we could actually we could see a three order of magnitude efficient algorithm. We proposed 3 magnitudes of, so this is the 3 orders of magnitude, and we were able to brought it down because we used a probabilistic algorithm, not a deterministic algorithm. But if you see on the left hand side, the starting point of all these curves are the same, which is around 10 milliseconds. So although we focused mostly on the revocation part of it, in order to make these privacy preserving schemes actually applicable in different applications, we need to also focus on the left hand side, which is the starting point of these, and we need to bring it down. So we are looking into that. We are looking into more schemes in which we could bring it down. So that is the direction of the future work. So that is the end of the talk. Thank you very much.
Questions? I think we should also enforce like at least 5 questions, as is the case in PCE seminar.
Yes.
Can we do some decision-making algorithms to come up with lesser false alarms? When instead of going with just 1 0 and then discarding it, can we do something more to come up with lesser false alarms?
Okay, so when we came up with this idea of piecewise orthogonal codes, the first thing was this is just a heuristic algorithm. We did not show that, okay, this is the algorithm which is the best algorithm to use. So the first part is to, so it is just a off-the-shelf thing that we found out, and we saw that, okay, there are no false negatives in it, so this should be the algorithm that should be used. First thing is that. Once you come up with possibly a better, so this is a piecewise orthogonal code, you might come up with a different design of these codes. You can come up with a completely different design. Then the second step would be what you are saying, that come up with a very efficient algorithm. Now, as far as this piecewise orthogonal codes is concerned, I think that making decision on just first 0 that you obtain is the best way to do it. But it may not be true for any other design that you may come up with.
It depends on the kind of
codes that you use, yes.
Then the threshold will change.
Yes, the threshold will change. It was just off-the-shelf type of code, and we took it because it had no false. That is the major concern. That was the major concern, that there should not be any false negative.
You are designing the codes itself, and we are checking on those codes, the same codes. The deterministic, like those pseudo codes, we are performing the correlations on the known sequences already. So we can make a restriction either 0 or 1.
Yes.
But if we are not designed that way, then we need to use some thresholds.
Yeah, so if they are not orthogonal codes, then the thresholds will be very different. Yeah. Yes. With orthogonal codes, it will be deterministic.
Then you can't guarantee.
Yes. Then you can't guarantee. So that's what was the problem with the probabilistic algorithm, that you can have false positive, but you cannot have false negative. Otherwise, we could have just used a random code, and the length would have been equal to 160 samples.
But if you consider noise, then also you cannot guarantee.
Yes, exactly.
Right? So, but if you do the actual system design, then maybe going to non-orthogonal codes might be better because you reduce the length. Right?
So
under the-
yeah, so that's a very nice point that you raised. So therefore, here we assume that there is no noise because we have developed two sets of algorithms. One was for embedding and extracting the authentication signal, and once you get those signals in bits, then there is this privacy-preserving authentication mechanism that you could use. So this is not embedding and extracting part of over the PHY layer. It is something after you have obtained, before you transmit it to a PHY layer channel and after you actually do a PHY layer processing. So this is not a PHY layer scheme. This is a cryptographic scheme that you use.
No, but still there can be errors, right? There can be, even if you use some sort of channel coding, still there can be errors which may linger on to higher layers.
Yeah,
That's the
that
whole
is true.
point, right?
Yeah,
So,
that is true.
you can't really limit the errors to, because of, let's say, noise to PHY layer. They may show up in the higher layer as well. Even if, let's say, you're using a long code word, one code word may map to another code word, right? So
Yeah, so what happens in cryptography is that even if your message has one bit of error,
Mhm.
so your message have thousands of bit length, but even if you make one error, you cannot verify the signature. So the message that you are trying to verify need not to have any error in it in order to make it in order to make this whole cryptographic algorithm to work.
But
So-
for this to work, you need to know that there was an error, and that depends on the type of channel code that you are using and its error detection and error correction capability. If you make more errors than what you can detect or correct, then there is no way for the receiver to know that there was an error.
Yes, then these cryptographic algorithms won't work if there is any error in it. So in that case, it will be just dropped or it will be just declared to be an invalid signature.
I think these can be encrypted further using another set of encryption, and that way we
So,
can.
so in an actual system, this is what happens. You have these kind of cryptographic algorithms built in. Then you have the MAC layer. There are so many
Right.
frame numbers added to that,
Sure.
and then you have these PHY layer things, error correcting codes, and then you transmit. At the receiver, you just try to use the MAC layer processing, the frame numbers, and you put them in sequence, all the whatever the message that you have received in different frames in sequence, and then you try to run this algorithm on it. If it does not pass, then all of them has to be retransmitted, or they will be just dropped.
Okay.
Because the cryptographic algorithms cannot be used with any error, even a single bit error.
Right.
Yeah.
So in the beginning of your talk, you mentioned that at the receiver, it basically goes through the signature of all the transmitters, right, and checks whether it's revoked or not. So is this done like for the entire group together, like all the transmitters, or if we can do it in an online manner, like per transmitter we do this, and then the worst case complexity, we don't have to look at the worst case complexity, maybe the average complexity of calculating the total time to see when it
Yeah. So what happens is the regulator publishes a list called revocation list, and it has the identities of all the transmitters which are revoked. Okay, so it has that complete list. Now, if a verifier receives an authentication signal, and now it needs to verify if that identity is present in that revocation list or not, it has to go through the whole list. Now there could be multiple types of algorithms that you could use. If it is, if the identities are in the signature and the identities are in the revocation list, then you could do many search. You can use any search algorithm, binary search algorithm. You could do it very efficiently. But in group signatures, what happens is the identity is hidden behind a function in the signature. Although the identities are in the revocation list, the identity is hidden inside a function inside the signature. So you cannot directly use any of the existing search algorithms to just come up with a very efficient algorithm to search the identity. So you have to go through them sequentially till the last one to actually make a decision that this one is not revoked.
In applications that we try to apply this scheme, right? For example, IoT and
Yes.
cellular. So, and you have really long codes. It would rarely happen that with the multipath effect and all, you actually receive that entire long code without a single bit error, right? So, because in that case, your error correction has to be perfect, like 100%. So,
okay, let me go back. Yes, you are saying the same thing that Dr. Dhillon was saying. So you are exactly right in saying that this big of a signal cannot be received at a receiver without any error. So if we just transmit this signal at PHY-layer, you cannot receive this big of a revocation code or authentication signal without any error. But what happens is you have these inbuilt, even if you have these inbuilt error correction codes, there are always some packets which are dropped at the receiver. That is why you see if you are receiving a video, there are interruptions in the video, or the quality of the video sometimes goes down because there are errors being made when you are receiving the data. So when you are receiving a data, you cannot verify, and there is an error made in a packet. So the packet length is something, let's say 1000 bits. If you receive those 1000 bits, you cannot verify those 1000 bits. You completely drop those 1000 bits. You will start with, you either have retransmission for those 1000 bits, or you just drop it.
there would be some kind of a checksum at the end, where
Yes.
if it is only beyond correction, then
Yes.
you would drop the packet.
Yes, exactly.
But in our case, it would be just 1 bit, right? So
Yes, so if it is below the ability of the error correcting code to correct, then it could be corrected, and then you will use these bit level operations. So the cryptographic algorithms are bit level operations. So once you have done all the PHY-layer schemes, you have already applied all the processes of PHY-layer, then you come for a MAC layer, and then you, so actually this, what is happening here is that I am skipping multiple layers here. So what is happening is, one scheme is at the PHY-layer, and this scheme, this authentication, privacy preserving authentication, you could understand that it is at the application layer. So I am skipping 2 layers between these 2 schemes.
So your assumption is that the physical layer receiver has actually corrected errors with a checksum of 100%.
Yes, yes.
Okay.
And there are 2 layers in between MAC layer and transport layer. So those layers have also performed well enough to ensure that what you are receiving at the application layer, where you are actually running this authentication scheme, every bit is a correct bit.
Okay, guys, if you have any further questions for him, I'm sure he'll stick around for a few more minutes. Thanks everybody for coming, and thank our speaker again.
Yeah, thank you.